Hi, my name is Guangliang Yang. I'm from Texas. I'm from Texas A&M University. Sorry, can't know how to use it. 1 second, please. I don't know how to. Go to next slide. Okay. Sorry. Recently in Android, the hybrid development approach is becoming very popular. It relies on the use of WebView, which is an embedded browser in Android. Using WebView, developer can directly render web content and run JavaScript code in Android applications. And in this paper, we refer to this type of applications as a hybrid application. And using this application, and the developer can get many advantages. For example, developer can directly reuse existing work. And here is this picture shows an example that an application wants to show the shop centers. Developer just need to integrate WebView and let the WebView show Google Map. It's very easy to use. Compared with regular browsers, WebView is more powerful by providing several unique features, such as event handler feature. This feature allows the developer to customize and handle web events that occur in WebView. It's very powerful. For example, developer can use this feature to customize the web UI, like an alert dialog. And use this feature, developer can also support some customized URL. For example, there is a link whose content is a tile plus phone number. If a user clicks this link, the app can directly make a phone call. In our study, we found this feature is very popular. Almost 94% of hybrid applications use this feature. However, also, this feature is very powerful and enrich the functionality of hybrid application. It also introduces several critical security issues. And I will use the pictures to show the problem. This picture shows the architecture of hybrid application. The top box is WebView, and the bottom box is native code, which is Java code in Android. To enable the event handler feature, developer must implement some native method in advance and register it to WebView to make it effective. And then in the runtime, if the web code triggers some web events, and these events will be handled by the registered event handlers. In high level, so the event handler feature provides a bridge that links the web layer and the native layer. However, the problem is that there is no access control on this bridge. Any code loaded in WebView can freely access this bridge. This problem has been discussed by existing work. However, it is still unclear how this feature is involved by attackers in practice. One potential attack pattern is that attacker may inject malicious code into WebView and trigger the event handler and access the content functionality. Use this picture to demonstrate this scenario. There is the left blue box is Android device, and the right side is a web server. In runtime, the web view will contact with the web server and loads its content. However, if there is some problem for the web server or the link between the web view and the web server, attacker may get some chance to inject malicious code into web view through web attacks and network attacks. And in this way, the malicious code is totally loaded in WebView and executed. And then the malicious code can access the bridge freely. And then trigger any event handlers and access their functionality if appropriate input is fed. So this is here is an example to show this attack pattern is feasible in real-world applications. We found this in a very popular advertisement library. And if in WebView, if attacker inject malicious link to it, and if user clicks this link, then a native method will be triggered. And here the native method name should override URL loading, and it has 2 parameters. The second parameter is exactly the URL's content. And in runtime, the URL content will be passed. More specifically, firstly, C1 and C2 is extracted from URL and then is converted to a target function. And then the function will be called with some parameters. And finally, the result will return back to the web space by calling a native function whose name named load URL. And in this way, if attackers give a very corrupt URL content, and attackers may get some chance to access any functionality inside the event handler. And if the event handler has some problem, that a serious concern may be caused. And I will explain more details here. And firstly, the URL contains C1 and C2 is extracted and converted to a real function. And there's a mapping shape relationship is saved in a real hash map object. And because the hash map, has a lot of arrays indexing operation, so there is an implicit flow. And then the function is called with some parameter. The parameter is also can specify the URL. And lastly, the result will return to a callback function. The callback function should be a JavaScript function, so that if attackers define some function, JavaScript function, and transfer the function name into the URL, and then finally the function will be called and to receive the result. In our finding, we found that this advancement library is very powerful, support many powerful commands. For example, recording audio and use a camera to take pictures. And I use this here to summarize this attack pattern. There is the event handler and there is a target functionality. To access this target functionality, attacker must let the event handler totally follow this path. And because attacker can totally control the input, so the functionality can be accessed by attackers in most of the time. But in some time, it may be very hard for attackers. For example, the second statement's path constraint cannot be satisfied no matter what input is given. So in this case, it's very difficult for attacker to leverage this functionality. But in the native handler mechanism, there still has some possibilities for attackers to leverage it. We assume that there is another event handler. If attacker triggers this event handler, firstly, the program state may be totally changed, and which may impact the path selection of the first event handler. So there is an event handler dependency relationship between the second event handler and the first event handler. So we define the second attack pattern as follows. So attacker can play web events as gadgets, just similar with return-oriented programming. We assume the target program state is ST, and it can be achieved through state transitions from S1, S2, and to ST. And this can be triggered through calling a sequence of web events, maybe from E1 to E2 to ET. So in this way, attackers can stake several events together and change the program state and finally access the functionality they want. In this paper, we generalize all these attacks based on event handler feature as event-oriented exploits. We call EOE for short. And in our study, we found that EOE causes lots of serious consequences. For example, may cause cross-origin DOM manipulation and cause phishing attacks. So it's very critical and important to detect and verify verify existing applications against EOE. However, the problem is that existing technique cannot or face a lot of challenge to solve this problem. More specifically, we can divide existing work into static analysis and dynamic analysis. Static analysis usually have very high false positives and may also have very high false negatives in the native handler analysis. It is because the extension of the implicit flows, just as I showed in this example. Existing work need to convert some part of the URL content to a real function, but the real function is totally saved in a hash map object. Because the static analysis has no real data, it's very difficult for them to do that. And maybe I can quickly pass this part and directly go to our solution. And instead we propose a new solution called EOEDroid. And EOEDroid consists of 3 stages. And firstly, we use symbolic execution to analyze all event handlers and to identify critical functionality that may be leveraged by attackers. And then we analyze the feasibility of each pass and to check if it is feasible to trigger the functionality in practice. And finally, we compare the results of the first stage and generate the exploit code to verify, to help researchers or developers to verify the problem. And I can quickly go through each module to demonstrate how they work. And in the first module, we use symbolic execution to scan all event handler and finally a pass, and then calculate its pass, solve its pass constraints. And then in the next stage, we can do static analysis backward to search how to change the program state to let it reach the expected state. And we use a backward analysis for each pass. And finally, we found this pass that can meet our requirements. And so there is a event handler dependence from second event handler to the first event handler. And in the last stage, I will show more detail later, maybe. For the first stage, we use symbolic execution. And symbolic execution is very it's classic technique, and but we solve many challenges. And deploy it in Android applications. And maybe because of time limitation, we can quickly pass it. And the second stage, we compute the pass constraints and generate the execution order. And in the last stage, to generate the event exploit code, we conduct a very systematic study about how to trigger event handler, how to transfer data from web space to the native space. And finally, we also need to analyze the JavaScript code to generate this callback function automatically. Here we just simply use the syntax analysis to generate AST tree and generate the code. And the results, we evaluate our system in almost 3,000 of applications and find almost 100 vulnerabilities. And this table has show more details. And here we use a very simple case to demonstrate how our system works. And it is a very high profile browser, and it contains very sensitive functionality. For example, read IMEI, and the developer may realize this problem and try to close it. However, using our system, we can still discover that there is still possibility for attackers to leverage this functionality. This is code, and we can quickly go through it. And firstly, the IMEI is read to a temporary variable, and then it transferred to another one. And finally, it's sent out through intent, which is intercomponent mechanism in Android. And in our analysis, we found it's maybe difficult for attackers to trigger this functionality because there is one pass constraint that cannot be satisfied. But using our analysis, and we found that there is still some possibility to do it. Finally, we found that there is another event handler can change its state, and we can generate this event handler execution order, and from the on page finished to should override should URL overriding, and finally generate the exploit code, and this is based on our existing study results, and so we can just map the event handler to the corresponding code. And finally, this is the exploit code that can trigger that vulnerability. And conclusion, we had also this is not a new problem, but we give a new insight about this attack and generate this attack. And finally, we give our solution to help researchers to detect and verify the vulnerability in existing apps. Yeah, thanks.
Okay, I guess I will start from with one question about the defense. Can you talk a little bit about like how do you plan to defend against this new event-based attack?
Because I mean, our paper is mainly focused on the attack part, and for the mitigation, we give several useful suggestions. For example, use HTTPS links, and that can reduce the attack surface, and use some new in the event handler that just proposed in the new Android version, because it's given new several useful and new information, such as the origin information that who trigger the event handler, something like this. Yeah.
More questions? Then let's the speaker again.
Okay, thank you.